So what I'm saying is we'll take this first number, we'll add it up, just the one of it. We'll call this S1 for summation number 1. We could add up the first two things. We call that the summation number 2. We could take the first 3 and add those up and so on. We would call these partial sums of the series. And we can even use the sigma operator if you like. So just like an integral says start at A, integrate up to B, this sigma operator is just saying start at I equals 1, add up until we get to I equals n, and then A sub I is telling us what is the number to add at step I. So these partial sums are themselves an infinite list of numbers. So they are a sequence. We took some list of numbers. We are attempting to add all of them up. And what we have is this sequence of partial sums. So the whole reason we care about convergence of a sequence of this list of numbers is that we can use that to determine convergence of the sequence itself. So if that limit of partial sums exists and is finite, then we'll just say that the sum, the sum of the infinite series is going to be equal to this limit. So this is a little small on this slide here, but if we have this series, what is A1 plus A2 plus A3 plus A4 and so on? How do I add those up? I will instead think about, I can calculate any of these partial summations. That'll get me a new sequence. If the limit of the partial sums exists, well then that means that my infinite sum, that's actually something I can assign a value to. So we'll call that convergent. And otherwise, if the limit is an infinite limit, or if the limit is divergent, then we'll call the summation divergent. So every one of these infinite sums is secretly a limit, just like the limits we were doing on the previous homework. Now, this has some consequences for the way that we're going to calculate the sum of a series, right? So it's one thing to have this abstract notion of, does this problem make sense or not? But I want answers. I want actual values I can compute. So let's dig in on a series with a very special formula called the geometric series. Now, there's lots of different geometric series with different parameters. Every geometric series has to start somewhere, so this one will start at parameter A, and for technical reasons, we do not start at 0. Now, the rule is, whatever the number A is, the number that comes after A is a multiple of A, so say A times R. The number that comes after that is A times R squared. The number that comes after that is A times R cubed, and so on. So there is this common ratio. Any two different numbers that are one apart in the series, the later one is some multiple of the earlier one, and it's actually the same multiple the whole way through. So think a half, a quarter, an eighth, a 16th, a 32nd, and so on. That's an example of a geometric series. So we completely parameterize these, knowing by where they start and what the ratio is. Well, first of all, let's figure out maybe my multiplier, my common ratio, is 1. Well, if that's the case, then my series just says A plus A plus A plus A plus A plus A, and so on. So each of those partial summations, each of those partial sums is getting larger, or at least larger in absolute value, right? A could be negative. So this partial sum is just going to be equal to n times A. So my sequence of partial sums would be the sequence A twice A, 3 times A, 4 times A, and so on. But that will diverge, because eventually it will surpass any bound that we try to put on it. It will go to either positive infinity or negative infinity in the limit. So what this tells us right away is that if this common ratio R is equal to 1, then the series diverges, right? There is no numerical value we can assign to that. Now, let's suppose R is not equal to 1. This is where we can have some fun. So there is a trick to figuring out what formula my partial sum should have. As soon as I have a formula for the partial sum, that gives me a foothold for what the series should look like, the whole infinite series. So my partial sum stopping at n looks like A plus AR plus AR squared, and I will stop at AR to the n minus 1 power. Right, so I have n number of things on this list. Here is item number 1, here is item number 2, this must be item number n. Okay, well, if I multiplied that whole sum by R, I can just distribute through. I know how to distribute through for finite sums. Then I would get, it would just kind of shift over, wouldn't it? I'd get A times R squared, and so on. And I get this A times R to the power n. So let me subtract the one of those from the other. That is telling me that the difference of that's telling me that this difference, Sn minus R times Sn, is equal to A minus A times R to the power n. So let's solve for Sn here. Sn's got to be A times 1 minus R to the power n divided by 1 minus R. Oh, so this formula tells us what is the partial sum we would have at every step along the way as we calculate this limit.